All righty, howdy folks, howdy, howdy, good to see y'all. All right, so we're gonna just keep moving a little bit further on our way here along. All right, so that's kind of a bright little light on me, isn't it? That's outstanding. Good lighting on that one. All right, anyway, that's not what matters anyways. So we talked about the extreme value theorem yesterday, right? We got introduced to critical numbers, and we got introduced to relative extrema, and as well as the absolute extrema. So we're going to keep going a little bit further and look at a couple other theorems, Rolle's theorem and the mean value theorem. Now, Rolle's theorem isn't, honestly, as we go into it, Rolle's theorem isn't nearly as important as the mean value theorem. The mean value theorem, well, now that's a big idea, right? But the Rolle's theorem, not quite as big. And honestly, the mean value theorem does everything Rolle's theorem as well, so it doesn't really matter. So we'll start off today with the Rolle's theorem. Here's what Rolle's theorem says. Okay. If a function is continuous on a closed interval from A to B, and it's differentiable on an open interval from A to B, oops, I need that right there. There we go. Let's change that instead of if. Let's say let a function be if f of A equals f of B. So when we plug in these endpoints into our function, if they end up being the same, then what Rolle's theorem says is then there is at least one number x equals c on the open interval from A to B, such that f prime of c equals 0. In other words, we have a critical number. Okay? So let me show you kind of what's really going on here with this. Okay? So I'm going to draw some graphs here, and we'll see if we can't try to, just like yesterday, see if we can't try to make sense of some of this. So here we go. Graph 1. Graph 2. Graph 3. All righty. So let me just throw some random variables on here. Whoop. There it is. Whoop. 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 And I'm going to make a different color coming across here, friends, like this. I'm telling you, friends, if you had car sounds or some sort of sound effect, man, while you're doing math, I'm telling you, you will have a more enjoyable experience. All right, just something to think about there. All right, whoop, whoop. All right, when in doubt, make your closed dots really, really big. And you're guaranteed then to make sure that you meet what you want here. All right, so here's what's going on. These x values here, we're going to make them A and B. Like that. All righty. So now what this theorem says, if it's a continuous function, in other words, if I'm going to go to A and my graph starts going up, somehow I'm going to have to come down. Likewise, if I'm going down, and if I know that f of A and f of B are the same value, then I know that I got to come up. And there's nothing that says that I may not be doing it more than once, right? I could be doing it more than once. Well, that was not good. Let's try that again. Could be doing it more than once. I keep messing up that last little part there, don't I? Let's try. Oh, there we go. Whee! There we are. All right. And so each of these values, f of A and f of B, they have the same y value. So what Rolle's theorem says is that it says, listen, let's just take some random horizontal line, because the horizontal line always has a slope of 0. And it says there's going to have to be some point where this graph on that closed interval has to have a slope of 0, a horizontal tangent line. Somewhere along the way, there has to be some point on that closed interval that's going to have a horizontal tangent line. At least one. Now, it could be more. Could have more than one. It could happen more than once. And if you look here, look, there's a point. There's another one down here. It doesn't mean that there's only one. It just means there could be more. There could be more than one. So you start looking at all these things a little bit here then. Rolle's theorem says if our two endpoints have the same y value, in other words, the same y value means that they're going to have some sort of horizontal tangent line, some derivative equal to 0 somewhere along the curve. And again, that kind of makes sense. Kind of makes sense if you think about it. So let's try this. So let's see if we can't do something with Rolle's theorem here to see if we can't give this some idea here. So verify on the closed interval from, let's go, how about -1 to 2, that there exists an x value for such that f prime of x equals 0 given f of x is equal to, and now here we go, friends. I got to come up with a wonderful function. I'm thinking this function today might be x cubed. I don't want to use green. I'm going to use black, friends. X cubed minus x squared minus 2x minus plus 3. Now, this isn't going to be like our extreme value theorem where we're going to say we're going to do the work, and when we're done, say what we found. We'll save it singing for next week. We'll get more. And again, but just for the fun of it, say what we're gonna do, and then we do the work. When we're done, we're gonna say what we found. We said. I know you guys are tired of it already. But I've got a whole lot more of it next week. So, anyways, here's our little key. As soon as I see right here that I'm trying to verify a derivative equal to 0. Verifying a derivative equal to 0 means Rolle's theorem. Now we've already done a verify thing. We've already said that when we're trying to verify a function value, so I'm trying to verify some f of x equal to some number, we said that's always going to be the intermediate value theorem, or the IVT. So this is one of our verifying problems, all right? But notice, we're not verifying a function value, we're verifying that a derivative equals 0. Although it would help if I actually spelled verify right. Wouldn't that help? That's what I want. There we go. Verify, there we go. So now if we're going to verify a function value, intermediate value theorem, verify a derivative equals 0, that's Rolle's theorem. Again, there's going to be another way that we're going to see to do that here in a second, but that's when Rolle's theorem applies, when you're trying to verify that a derivative equals 0. Now, Just like the intermediate value theorem, this is an existence theorem. We're not going to solve it. We will never know what this is. All right, but that's essentially what we're doing here. So let's figure this out. I already know it's a closed interval. Yeah. I know that this function is going to be closed or continuous on the closed interval, and it's differentiable on the open interval because it's a polynomial function. The only thing I don't know is what is f of -1 and what is f of 2. Because according to Rolle's theorem, as long as these two values are the same, I'm actually almost done with this problem. That's how quick this actually is. So when I plug these in here, what value would I get, friends? Yeah. So if I plug them in here, what value would I get? It kind of looks like I'm going to get 3. If I plug 2 in here, I'm going to get 3. Well, now I don't have to do anything else. I'm just going to essentially restate the theorem with what I want it to say. And again, this is an existence theorem. It will never tell me what the value is. It just tells me that it exists. In other words, I'm having some interval from -1 to 3 for this thing. There's going to be some critical number on here. So let's try this. Since f of x is continuous, on the closed interval, differentiable on the open interval, and f of -1 equals f of 2, then by Rolle's theorem, there exists some x equals c from -1 to 2, that's supposed to be a comma, there we are, such that f prime of c equals 0. Again, we don't know what it is, but we know it exists. Notice the statement is really close to our statement for intermediate value theorem. It's really close. Really close. And if you graph this graph, we don't necessarily know what goes on here per se. But I mean, I think it's safe to say we could probably speculate it there a little bit, at least a little bit. So we have our values here when they're equal to 3. There's going to be, like, since this is a cubic function, it's going to look something kind of like that potentially, something like that. Because these two y values are the same y value, we could speculate that there would have to be potentially a relative max that's going to bring our curve down to the other point. We don't know what it is. We just know that it exists. If we wanted to find what that value is, if we wanted to find it, we could. If we wanted to find it, we could do that. I mean, it wouldn't take a lot of time. We weren't asked it, but if we wanted to, we could. We just have to find the derivative. So we just do a real quick product or power rule here. So 3x squared minus 2x minus 2. And then we'd set that equal to 0. And from there, we would do the quadratic formula, which I'm not going to go through and do, and take the x value that we find off that, because again, we'd get 2 x values. And one of those 2 x values we would take the x value that would fall in our domain here. And I'm not going to go through and figure out what that value is, but we do the quadratic formula to figure out what that our two x values, and one of those would have to fall in that -1 to 2. So we could go and find it out if we wanted to. But Rolle's theorem, that's not what it's saying. Rolle's theorem, just like the intermediate value theorem, is saying just show me. Show me that there is one that has to be there. Just show me. Doesn't do anything else. It just says, just show me. Okay? So, intermediate value theorem verifies the function value exists. Rolle's theorem, it verifies that a derivative equal to 0 exists. So let's try the Rolle's theorem one more time here. So let's get rid of our, didn't want to do that. Sometimes Magic Eraser gets a little bit excited. I get that. It's a lot of fun with Magic Eraser. Whoop, whoop. Whoop. All righty, so let's have you guys try one more of these just to see what you can do. Verify on the closed interval from 0 to, let's say pi. I don't have to come back and put a pi in here in a second. That there exists some x value such that f prime of x equals 0, given, and then I got to give you the function. So here's what our domain is. It's going to be from 0 to pi. Because again, just because we can do it with polynomials, we could still do it with any function. And our function, the whole function doesn't have to be continuous or differentiable. It just needs to be continuous and differentiable on our closed interval. Same thing that we saw with the intermediate value theorem. The whole function doesn't have to be continuous. It just had to be continuous on the closed interval we're dealing with. All right, friends. So do me a favor. Go ahead and pause the video and see if you guys can actually try it. See if you can do Rolle's theorem down to the Rolle theorem. You don't need to find the value. Just see if you can actually do it to the statement. All right, let's see how you did there. I went ahead and drew a graph here because I want you guys, when we get done with this, I want you to make sure that we see where it comes from. If I plug 0 in here, I get 2 plus sine of 0. And sine of 0 is 0. That means this is 2. If I plug pi in here, I get 2 plus sine of pi. Which is sine of pi is 0, so that would equal 2. So Rolle's theorem applies because I have the same value. So if I were to draw these points here, oh, looks like I got a little short. That's why I use magic pen. So if I were to draw a horizontal tangent line, or if I draw my tangent line, notice it's always going to be a line, horizontal tangent line equal to 0. There has to be some other point in there where the derivative actually equals 0. Doesn't tell us what it is. I mean, you could guess that's going to be at pi over 2. Doesn't tell us what it is. It just tells us that it's there. Okay. So now we write our statement. Since f of x is continuous from, and now we're going to use our close, from 0 to pi. Closed interval for continuous. Make closed, starts with C. Continuous starts with C. They go together. Differentiable means you can find the derivative on that interval. Differentiable from the open interval, 0 to pi. And f of 0 equals f of pi. Then by Rolle's theorem, there exists some x equals c from 0 to pi, such that f prime of c equals 0. All right, and again, how do we know we were using Rolle's theorem again? We were asked to verify. And the other reason why we know we're using Rolle's theorem, we're verifying a derivative equal to 0. So that's the first of the two theorems. And this is a minor theorem. If you don't remember this theorem, that's actually okay, because the mean value theorem will take care of it for us. Okay? I've only seen Rolle's theorem come up a little bit now and then on the AP test on a multiple choice or a free response. However, every single time you could have used Rolle's theorem, the mean value theorem would have worked just fine. So let's take a look at what the mean value theorem is. And so this one is a huge idea, right? Huge idea. And first of all, one of the ways we know it's huge, there's only 3 abbreviations we use in calculus. We had the intermediate value theorem. We had the extreme value theorem, which I don't recommend you use that. I don't like people ever using that abbreviation. We weren't allowed to use it forever, so I'd rather you not use it. I still have a hard time wrapping my head around that people do use it now. I'd rather you not. No reason to. Intermediate value theorem, extreme value theorem, mean value theorem. Okay? And for a couple of these, we've already said, at least for the extreme value theorem, we like this one because this one verifies a function value exists. So this is what the IVT does. It's a big one for us. It verifies that a function value exists. Well, mean value theorem is going to do something very similar to that. It's a big theorem as well, but it's not going to verify a function value exists. It's going to build upon what Rolle's theorem started to do. Rolle's theorem verified that a derivative equal to 0 exists. Well, the mean value theorem, it verifies any derivative value exists within reason. And I'll tell you what I mean by within reason. Okay. It verifies that a derivative value exists. So if you're ever asked on an AP test, does a function value exist? Boom, automatic IVT. But if you're ever asked if a derivative exists or to verify that a derivative exists, automatic mean value theorem. Well, here's what the mean value theorem says. And again, it's an existence theorem, just like IVT and Rolle's. So it's not gonna prove anything for us. It's just gonna verify that something does exist. And it doesn't tell us what that is. It just says something will exist on a domain. So let f of x be continuous on the closed domain A to B and differentiable on the open interval from A to B. Kind of looks like Rolle's theorem, right? It basically says there must exist some x value on the open interval such that f prime of that x value, so we're going to go and call it C, equals f of A, B, minus f of A all over B minus A. And the astute math student math students you are, you know exactly what this thing is that we're looking at here, right? I'm sure you do. And if you don't worry about it. It's okay. What we're really asking for here is, and we've said this many times when we've gotten together, a derivative, and this is slope. We say that a derivative is instantaneous rate of change, and a slope is average rate of change. So in other words, what this is saying is that somewhere on that interval, the instantaneous rate of change equals the average rate of change. Instantaneous rate of change equals the average rate of change. Or another way to look at it is that the derivative equals the slope, or the slops, apparently. This right here, friends, big, big, big idea, right? So in other words, somewhere we have on any interval that's continuous and differentiable, the instantaneous rate of change is equal to the average rate of change. And I think you guys can kind of see this as well. So let me see if I can't draw this for you. If we can get our mind to wrap around this, then we're going to be sitting pretty darn pretty here. All right. Let me go ahead and draw a couple of little segments here. Whoop. Whoop. All right, and I'm going to call this, again, A and B. All right, and let's see here. We're going to make that put a couple endpoints here for A and B. There is our two endpoints, and I'm going to make something like that. So here's what this says. The average rate of change, this is slope. And going all the way back to middle school, you guys found slope by using, that was horrible, wasn't it? Let's try that again, friends, here. What if we went like this? Perfect, much better. All right, so there's our average rate of change. You have your slope triangle that gives it to you. All right, we can figure out the slope, the rise over run of that. What this theorem says is, if that's my average rate of change, that there has to be some other value on that where that instantaneous rate of change is equal to the average rate of change. So this C value right here, it's going to have some sort of derivative value that is going to be equal to the slope of the endpoints. So f prime of c equals f of b minus f of a. So somewhere, somehow, and friends, you can kind of see how Rolle's theorem is essentially the same thing, because if the f of b and the f of a, if they're the same y value, you're essentially subtracting the same number. Anytime you subtract the same number, it's 0. So 0 over b minus a would be 0. So the mean value theorem really is, or the Rolle's theorem is really just an application of the mean value theorem. Okay, so again, we probably won't ever use Rolle's theorem again. I mean, we'll do a couple problems just so you have an idea of it, but the mean value theorem will do everything for us. So let's try a couple of these and see if we can't try to bring this whole thing together. Intermediate value theorem verifies that a function exists. Mean value theorem, and we're going to call it MVT, verifies that a derivative exists. I don't want to get rid of that quite yet because we'll use that to model our statement off of. Here's your problem to begin with, friends. Verify for f of x equals x cubed minus x squared plus 1. I'll add the exponents here in a second. Verify that there exists an x value from -1 to 4 that has f prime of x equals 10. So we are going to verify a derivative value, and that should be not that. That'll be x cubed and x squared. And again, how do we know we're doing mean value theorem? We got our two key phrases here. How do we know? It's the phrase verify and derivative. When you're verifying a derivative, mean value theorem. Okay? So, just like it's a polynomial function, just like it was last time. So therefore, great. We know it's continuous. We know it's differentiable. All I have to do is I can literally, honestly, at this point, jump right on into it. Okay? There's no waiting here. We're going to jump right on into it. As long as I know that it's differentiable and it's continuous, I have nothing else I need. Since f of x is continuous on the closed interval, and differentiable on the open interval, then by the MVT, the mean value theorem, there exists some x equals c from -1 to 4, such that, and this is where we're going to use the right to our formula now, such that f prime of c is going to be equal to f of v, so in this case f of 4, minus f of -1 all over 4 minus -1. So we're going to plug these values in now. And right now, we don't necessarily know that it's going to be f prime of x equals 10. We're guessing that it is. So if I plug in 4 into my equation here, so if I plug in 4, what do I get here? I get 64 minus 16, that'd be 48 plus 1, that'd be 49. So if I plug 4 into my original equation, again, I'm plugging it into this equation right here. That's 49. F of -1, if I plug that into it, friends, I'm going to end up with a -1. 4 minus -1 is 5. So 50 divided by 5 turns out it equals 10. And whenever the College Board asks you to verify, it will be that a derivative value, the mean value theorem will give you that value they're asking you to determine. Again, it's an existence theorem. We don't know the value. We could figure it out. As a matter of fact, I think we should, but I want you to see it. We don't know that value. All we know is that it exists. So just for the fun of it, if I ask you to find it, okay, so how do we find it? Just like before, how do we find it? How do we find it? Well, what does this say? It says I'm going to have a derivative. I know the derivative somewhere is going to be equal to 10. So we would essentially, if we want to find this, we're going to go back where our derivative is, our function is, and we're going to find that derivative. So f prime of x would have been equal to 3x squared minus 2x plus 0. Plug 10 in. Three x squared. I don't know what it's going to be, but I know that I have to have at least one value on my interval that would have it. So if I had to go and find it, I could. Again, very rarely are we ever asked to go find it. And then from there, we go ahead and do the quadratic formula now. I'm going to actually do it this time. I want you guys, we didn't do it with Rolle's theorem, but I do want you to actually see how this whole thing plays out. So -2 squared, so x equals a negative b plus or minus the square root of b squared minus 4ac all over 2a. That's 120 in there. Divided by 6. And friends, when I plug this in, the two values I get, at least one of them, they don't both have to go in, but at least one of them better go in. So that's going to end up being a negative 1.5226 and 2.1893. All the mean value theorem says is that there's going to be some value on my interval that would work. So do we have a value? So what was my interval? It would be -1 to 4. Turns out I do have my one that works. Now we don't need to go further than that, but if you did have to, that's how you would go further than that. You would go ahead and solve it, find your derivative, set it equal to that derivative value you were given, and solve it. But again, the mean value theorem, it doesn't require us to figure out what that value is. It just says prove that there is one. Prove that there is one. So let's have you guys try one yourselves. And then after that, we're going to go ahead and call it a day. Oopsies. Started erasing things. I get really excited about erasing. I start making things disappear a little too quickly. Let's get you guys going on this before I actually erase the rest of it here. There we go. What I want you guys to do is, given f of x equals x to the 4th minus x squared minus 2, verify that f prime of x equals 4 for some x value on on -1 to 2. And let me write in those exponents there. There we are. I have x to the 4th. So given x to the 4th minus x squared minus 2, verify that f prime of x equals 4 for some x value on -1 to 2. Go ahead and pause the video, and then we'll solve it. All right, let's see how you guys did, friends. Here we go. And again, remember, as long as it's continuous differentiable, we can go jump right on into it. Since f of x is continuous from -1 to 2, and differentiable from on the open interval from -1 to 2, then by the MVT, there exists some x equals c from -1 to 2, such that, and here we go, f prime of c equals f of b, so f of 2, minus f of -1 all over 2 minus a -1. So f prime of c equals, if I plug 2 in there, I get 16 minus 4, that's 12. Oh, that'd be 10. If I plug -1 in there, oh, what would that be? I get 1. I get 2, I got 16 minus 4, minus 12, minus 2 is 10. All right. And if I plug -1 in there, I get 1 minus 1 minus 2, so minus a -2. I had a little arithmetic mistake in my head there. I was going, wait a second. All right, and f prime of c, that would be 10 minus 2 is 12 over 3. And friends, MVT says there will be a c value then that will have a derivative of 4. That's the MVT. So friends, general thing to take away here is, if you remember nothing else from today, this right here, at least the IVT and the MVT, that's big idea time. You want to prove that a function value exists? IVT. You want to prove that the derivative value exists? MVT. All righty, friends. Well, good luck. Enjoy your weekend, and I will see you guys on Monday morning. Take care.